Hopefully everyone's feeling fresh and caffeinated, especially Gilad. So Gilad will have his third lecture of 3, and then tomorrow he's leading a discussion, so there's not really going to be any prepared notes tomorrow, but you should be prepared with questions for him.
Yes. It's on.
The camera.
Ah. Thank you. All right. Yeah, so I hope that you managed to find the notes, the slides. I update them to include the today lecture. So you'll find the homeworks there, so we can discuss it tomorrow. And also, of course, it's impossible in 3 lectures to cover what I really wanted to convey. So you'll see stuff which is not covered during the 3 lectures. You can ask about this tomorrow. So the starting point is here. Remember that we wanted to try to think about how to address the situation that we're at, the fact that we have some conceptual soft principles that might tell us a little bit more about the scale of new physics, because otherwise the space of solution is too diverse. And one particular thing that we are focusing in this 3 lecture is the naturalness problem, but remembering also the idea of the quality problem. And we discussed the last week, you discussed the conventional models that require TV new physics. Then we kind of started to think deeply about this shocking proposal by Weinberg about the CC, that actually you don't need anything. There's no scale of new physics unless you go to the Planck scale where you find the landscape, etc. So this is through the anthropic solution. We actually discussed also that for the Higgs mass, there might be a similar argument to Weinberg that if we just change the weak scale, indeed you can have an anthropic bound, but we saw that it's not robust by constructing a counterexample, the weakless universe. So the question that we want to consider today is there maybe a hybrid model that is not solving the naturalness problem in a conventional way, so don't expect to find TV new physics, but still through some cosmological evolution or cosmological dynamics of the fields, we'll see that we can address the hierarchy problem. And then the second part of the talk, we'll try to understand what kind of phenomenology this leads us to and what kind of experimental signature. And I'm going to stick to one framework to consider this, the relaxion, because it's very concrete. The other ones are a little bit more abstract. But for the relaxion, we can literally write 1 or 2 lines Lagrangian and follow it within the assumption of it and derive basically the dynamics and then talk about the phenomenology. OK. So for now, just to connect directly from where we stopped last time, we need to talk about evolution of scalar field. And when I'm saying evolution is through the cosmology. And one, the canonical example that we'll have in mind is the inflaton. Which is under the, if you wish, conventional model of inflation. Basically, we have very flat potential. The inflaton is slow rolling. So here is the inflaton. It's slow rolling rolls through the flat potential for many, many decades of time. So what we call E-fold. So the universe is expand exponentially e to the ht with the time which is roughly 60. So it's doubling its size 60 times to solve a cosmological problem, which I'm not going to describe. I'm sure that Jay described it to you. And then after some time, it actually falls into a well and start oscillating and reheat the universe. Now, what we also said is that, in fact, because during this time we have very large dark energy or cosmological constant, yes, if the minimum is here at 0, okay? This height is very high. That means that we have Hubble, which is basically equal to, so Hubble squared is basically equal to the value of V phi squared, V phi divided by m Planck squared. So this is effectively, because it's almost constant, this is effectively behaved for us as a cosmological constant in a very early epoch of the universe, and the universe expands. So we are living, when we're describing the evolution, in a time-dependent background. So it implies that if we convert this using the analogy, and you can make it very precise, of converting the Hubble expansion rate to temperature, which is called Gibbons-Hocken temperature, then we can think about the field here as not strictly localized as a delta function because it has a stochastic motion, and therefore we can think about it, let's say, as a Gaussian, which is moving. And to describe the motion of this, we wrote the Falcon-Planck equation. Which basically describe the probability distribution of this field phi as it evolves, okay? So there was probability distribution function P of phi and T, and this probability distribution is really normalized. So if I want to consider all values of phi, then P d phi is going to be 1. And the equation was, again, d phi times 1 over 8 pi squared d phi h cube p plus dv dp, dp dA. Sorry, 1 second. V prime p over 3h, and this is equal to dt dp, okay? And this is an equation that you find in many, many branches of physics when you have a stochastic term plus just a drift term. And you can see that if you take basically h to become very small, it will be dominated by just the drift term. So this is just describing this classical evolution. But when you make h very big, this becomes less and less important. And this is the stochastic term, which is basically spreading a random walk values for the probability distribution. So it means that the phi here, instead of moving like a delta function, is spread around. Okay. Now, this is all fine. But then what people were doing, and it's become more fashionable again in the last 10 years, they say, okay, let's just not weight the evolution of this scalar just by its location, because there's one more thing which is going on. There's inflation. So, you know, the volume of the universe, as we said last time already, is changing dramatically, exponentially, when this field is moving. So for example, let me just exaggerate for a second. Suppose that I'm looking at such a potential for the scalar. So naively, classically, you would think that the field will move down, and maybe there will be some spreading during the inflation. But if you now think about it in terms of what happened to the volume of the universe, actually, it could go down, but because of this stochastic motion, then it spread also uphill. And now, okay, so I'm writing here dash, so remember that it's a quantum mechanical effect. But when the field is spreading also uphill, then the expansion rate, which is just equal to V of phi, is bigger uphill. So here the expansion rate is bigger than that. of the central value, the classical value. So we have a weird situation that the universes which are obtained by the quantum spread of this field, if it's going uphill, their volume is expanding faster, which is very, very counterintuitive. But that's a fascinating phenomena. It was actually observed a long time ago by Linde, I think, for the first time. And then people propose, let's actually weight the probability distribution of phi not only by the evolution of classical plus quantum, but let's make a weighting which is by volume, something like that. E to the 3ht, okay? Because this is exactly how the volume, okay, cubic of the expansion of the universe is e to the 3ht. Okay, so you want to define now a new probability function, which is not a probability anymore, because you see that, of course, this is not normalizable anymore. But this is now, if you wish, a modified, sometimes people call it PV in the literature, a modified probability distribution. And when you go over the Fokker-Planck equation, there's a new term which appears here, which is now, so now let me put here a V, okay, to remember that it's not more the probability distribution function. And now there's another term which is entered, which is just linear with the Hubble. So you see, it gives advantage in this differential equation to places where h is big, uphill. And there were several papers recently that used this to connect the evolution of the fields with the Higgs to critical points. Because what happened, suppose that I have something like that, and this is the system also describing the scalar and the Higgs. I will not go into detail. I just wanted to give you the idea. And here there's a, if you wish, here there's a sharp difference in the potential. Maybe there's a big fall. So what happened is that universes will depend on whether this term is more important or that term is more important. They will decide whether they effectively go up and down because of this volume, extra volume support. So they can find themselves here in the critical point. Then after the fall, maybe it leads to a universe which is crunched, so you can ignore it. And the implication is that there will be a locus of, if you wish, point for this scalar system that will be found here. So if you relate this evolution both to the scalar and the Higgs, you actually find something which resembles what we discussed yesterday's lecture, that when we look at the Higgs top phase diagram, we saw that the Higgs mass is exactly at the critical point. Okay? So somehow, if you have evolution like that, and you can connect it also to the Higgs sector, then you find that this phi will be found in a place that if the Higgs mass, let's say, is a function of, or the Higgs quartic is a function of phi, you will find the parameters of the Higgs exactly at the critical point. Okay? And they even show concretely that indeed what's happened. So there's a series of papers and the references you can find in the literature. This is called the self-organized criticality. So let's call it organized criticality. Now, however, yes?
Can you explain again the logic behind this transformation of taking this Gaussian as a deformant, the volume? What's the logic behind it?
So this is just telling you the evolution of the inflaton, okay? But it doesn't tell you about what happens to the patches which are now created by the motion of this inflaton, okay? So for example, if you look at something like that, you understand that there is this spread of the value of phi, right? So you have non-zero probability now to find phi here or here.
Yes, but up to 5 minutes ago, the spread was Gaussian. Think about it as Gaussian, and now you're deforming it and you prefer...
No, it's still Gaussian. It's still Gaussian. Yeah, but now what I'm asking is a different thing. Okay, so I have, the evolution is still Gaussian. okay? But what happens to the, if you wish, if you do now a measurement, what is the expansion rate for the scalar which is here and here? The expansion rate is very different, okay? So this region expands exponentially much faster than that. So you can think, I'm not going to support this, I'm just going to present it. You might think that universes which have a very large volume will become more probable than the universe with a smaller volume. So in order to quantify this, let's just change the probability and redefine it, rescale it by the volume, and see now what happened to the evolution. And what you find is that if the parameters of the potential are such that this term is more important, sorry, this term is more important than that term, you'll find that there's the probability PV, which is not really a probability, but PV is now localized totally in the critical points. And these critical points usually are at the top of the potential and not at the bottom of the potential.
That's why I don't understand. You relate the probability to find such a universe, such a path, to the probability of finding the infant in a particular place in its potential.
Yeah, so it's I don't want to defend it. I'm just saying that this is interesting that these are much bigger, these are universes with much bigger volume. Now, I think that what you're hinting is related again to this measure problem that we discussed before. Do we care? Okay? Do we care that the region where phi is here has much bigger volume than the region is here? So that's I think, it's a complicated discussion. For example, when we introduced the Weinberg argument, it was true that if our volume is very small, it means also not only the length, also the time is very short, there will be not enough time to create complexity. However, here, I'm just talking about the primordial epoch of the universe, very early during inflation, right? So it's not clear how to relate this to Weinberg argument, because Weinberg argument is talking about what happened after inflation. In order to make this, in order to make the connection, you need to, if you wish, track this inflation through what they call the reheating surface, exactly what happens at the end of inflation, and to see what's the status of that. And then there are all kinds of discussion you can do if you connect this to the reheating and to the rest of the evolution of the universe, reheating and then matter domination, etc. You can now see whether indeed the universes with bigger volume indeed contains more complexity, or in the usual counting, more baryons, okay? So that is the thing which I think is the weak link in that, because it's not clear necessarily that here you have more observers than that. Okay, you need to weight it by the number of observers. Because this could be huge universe, but could be totally empty, where this could be smaller universe, but with more observers, okay? So that's the step that you need to do. Now, I don't want to get to this discussion. But nevertheless, I don't think that it would be, I don't think it would be good for education if I'm not going to mention this at least. So there are many ideas that are associated with that. Let me just mention a few of them. So the first thing is just what I said here. So you link. The first solution is basically link the Higgs evolution to the corresponding volume of the, if you wish, corresponding patch during inflation. And the easiest thing is, for example, if the quartic is function of this phi, Okay, then indeed, and you have volume weighting, then you can find that you are exactly the point where the quartic is very small, so you are almost in the critical point, as we see in the Higgs top. So there are many papers that are trying to do this kind of thing. Other approach, which is radically different, is to say that there's just a new formulation, if you wish, of the natural problem, saying that if the density of states is big or small, that's what you call natural or unnatural. It's completely different than what we discussed so far. For example, Dvali has several papers about that. And so if you arrange that the density of states is inversely proportional to the Higgs, mass, then you would naturally be driven to universes where the Higgs mass is very small. Because if you can arrange that the density of states is big when the Higgs mass is small, then naively you would think that it's more probable to be in the universes where the Higgs mass is small. So this explained, this lead to small Higgs mass. So it has nothing to do with criticality. But it's related to the density of states. And again, there are many, many solutions like that, okay? Yes?
Density of states or what?
It's like density of universes. You can think about it. I try to avoid this, but yeah, you're right. Yeah, if you push me to the corner, they are saying that if you think about distribution of patches, there's some mechanism. I can tell you, but this will take us another 15 minutes, which I don't want to spend. But there's a mechanism to create a situation that when you scan over the parameter of the multiverse, you find that there are many more universes where the Higgs mass is small compared to universes where the Higgs mass is big, okay, which is counterintuitive. If you arrange such a thing, then if you believe this criteria, then it's another way to solve, if you wish, to explain the mass hierarchy. Again, notice in all of this, not necessarily we introduce low energy physics. Maybe here you have to because you need to play with the Higgs parameter, but here you wouldn't see anything as a low energy observer. And I think that the last thing that I'm going to mention here, because it's very different than the other before we talk about relaxion, so the third point below here, I will continue all the way here. Or maybe I will leave this. Yeah, so I will go here. Is a work which is called Naturalness. That one is in the direction of, already in the direction that we will take, because it's assumed that you can kind of separate the landscape scanning from the evolution of the inflation. And the idea of naturalness is that suppose that you have an inflaton, or a heaton they call it, some phi, which at the end, at the end of inflation, it needs actually to transfer its energy to the standard model sector. And what they did in that paper, they assumed that there are many, many sectors. All of them are just copy of the standard model 1, standard model 2, standard model 3, standard model n. And what was the difference between all of these copies? The mass of the Higgs, okay? So in each of these, there was a different mass of the Higgs. Again, it's not easy to arrange such a thing, but let's assume that you arrange it. Then if the inflaton mass or a heaton mass is small, then it can only reheat to the standard model I in such a way that the sector here, which has a very small mass for the Higgs, because all the spectrum of the standard model is dictated by the Higgs mass. The masses of the quark, the masses of the W, the mass of the Higgs itself is related to the mass of the Higgs. So if here what's actually, you are varying the mass of the Higgs. You can arrange a situation where you have many sectors with different mass of the Higgs, and there's the mass of the reheaton or the inflaton is limited, then it can only reheat into the standard model I such that the Higgs mass, mh squared, let's say, is much less from the mass of this reheaton. And that way, it's not that you explain the hierarchy problem because of any fundamental principle, it's just because of the fact that you can reheat the standard model sector. So there are many copies of the standard model, but the actual universe that we are seeing consists only of the sector of the standard model because that's the only one which was reheated, okay? If you wish, it's a little bit like thinking about the pure axion model. The axion is very cold, and if we wouldn't have any coupling between the axion and us, then the axion sector will never be thermalized, so we wouldn't know that it's there. In that case, it's all the other standard model sectors. So only our standard model, because it has low mass Higgs, can be reheated. So this is why I wanted to mention it, because it's radically different.
Can you just move the problem to why the inflaton has this low mass? It's also scalar.
Yes, you're right, but they address it. Yes, they address it, but then it's much easier because one of the major problems of the Higgs is that we know that it has a very strong interaction related to the top Yukawa, right? If, on the other hand, the Higgs had very, very weak coupling, then there wouldn't be a problem associated with the hierarchy because then it's approximately a free particle, right? So in a non-interacting theory, there's no problem to understand why a scalar has a very small mass because of scale invariance being non-anomalous. So if this coupling is small, then you can actually protect the mass of this scalar. But for the Higgs, we don't have this privilege because we know that the top Yukawa is order 1 and the SU2 weak interaction has coupling, gauge coupling, which is order 1. So the scalar normally is very big. So we cannot avoid the fact that the Higgs is not protected.
But then would you have a reading of also all the standard models with less than us? That's what happened with them?
Yeah, so true, yes. So the dirt under the carpet is the fact that they arrange a model such that the scanning of this is not very small. So it comes in jumps of a few tens of GeV, okay? So this is a young field, so not everything here is perfect, but yes, you need to address this indeed. Okay, now, already here you see that it's maybe a bit naive approach, but you see here that you decouple all these issues that we saw before about the quantum evolution and eternal inflation, and you have a concrete field theory. So what does it very nicely is the relaxion. So now I want to switch gear and describe to you the relaxion mechanism, because again, it's very concrete, and it's, I think, much more elegant than some of the other solutions. So now let's be a little bit more specific. Now we'll try to do some real calculation. Good. So first I'm going to just explain to you the rough idea, and then we'll write the actual formula. So how the relaxion mechanism works? First of all, we assume that we have an inflation sector. And during the inflation, the inflaton is usually slow rolling. And also, it dominates the energy density of the universe. Okay, so far it's standard, normal inflaton sector. Again, the same picture that I drew to you several times. But then we introduce only one new scalar, and that's the relaxion. So introduce one new scalar, and it's not just a scalar, it's an axion, new axion. So namely, I don't know if you already had a chance with Raffaele, but you will discuss it, if not today, then tomorrow. So we introduce one new scalar, an axion, which is protected by a shift symmetry. Did you discuss it already? No, but I'm assuming that you know a little bit of axion physics. If not, I apologize, but we cannot, squeeze everything in 1.5 hours. So it's protected by a shift symmetry. Namely, in the limit of the exact symmetry, A goes to A plus C is a good symmetry of the Lagrangian. And it's not strictly an axion, it's a pseudo Nambu-Goldstein boson. So we'll have some breaking of the shift symmetry. For example, because it couples to, because it's protected by symmetry, which is anomalous, so it is generated by QCD instanton, for instance. Okay? So now, the only non-trivial ingredient is that the mass of the Higgs, so, okay, let me be more specific. So usually, in the Lagrangian of the Standard Model, we have the negative mass of the Higgs, which is responsible for everything, electroweak symmetry breaking, all the masses, etc. Now what we are going to do, we are going to promote this mass to a function of the relaxion. Okay, so the QCD, so you can think about many ideas related to that, but basically the mass of the Higgs is becoming function of this axion. Is this surprising? Not really, because even if you think about the Standard Model QCD axion, then you know that the potential of the axion so the potential of the axion is actually a function of m pi squared, f pi squared times cosine A over f. And I apologize for the fact that I'm using stuff that maybe you haven't seen yet. And we already used, in fact, when we explained the Wickless universe, the fact that m pi squared is a function is equal to m up plus m down times f pi. And m up and m down, as we already discussed, are equal to y up h plus y dh. So here we see that the potential, maybe I should write it as A, sorry. The potential of the axion itself, this celebrated axion, is a function of the Higgs. So this shouldn't be shocking that I can write, and that's easy, I can write a theory where the mass of the Higgs is a function of the axion. Okay. Now, in addition to the fact that I promote the mass of the Higgs to something which depends on the field, there's also what we call a rolling potential. So there's another potential which has nothing to do with the Higgs, just for the relaxion, which I'll call phi. Okay, there's basically another term related to the potential of the axion, which I can just write as I don't remember how did I write it here. And just be consistent. Okay, I just wrote it as m to the fourth times cosine phi over f. And I'm already using some sector which breaks the symmetry of the axion potential. And when you break the shift symmetry of the axion with compact variable, it's just an angular variable, then it always gives rise to trigonometrical function. This is why I write it as m to the 4 times cosine phi over f. And then I have one more ingredient, and we are done. Yes, Chaya. I'm using now, because you'll see, yes, I prefer, because you'll see that it behaves as a scalar dominantly, I prefer actually not to call it A, and I apologize for that. I prefer to call it phi, and it's not the inflaton. From now on, let's forget about the inflaton. So from now on, phi is the relaxion. So let me just write. So phi now is equal to the relaxion, because otherwise the notes will be, I will be inconsistent with the notes and also the literature. So we have the inflaton sector. It's standard. We forget about it. From now on, our only degrees of freedom, the new degree of freedom will be this phi, which is the relaxion. Apologize. Yes, it's still, even though I call it phi, it's still protected by a shift symmetry. It's an axiom. And now the only last ingredient that I have is when I look at this mass, when I look at this mass term for the Higgs, it's actually made of two terms. So there's one, something which is, how will I write it? Let me just write it explicitly, and then it will be easier. So I want to write just the mass of the Higgs as a function of phi. So I want to write it like that. So lambda squared minus capital M squared cosine phi over f, capital F. And then plus or minus, it doesn't matter, something which is small m squared times cosine phi over f. So that's not exactly how it explained in the original paper or in some of the literature, but I already want to write it in a way that will be healthy and easier to understand if you will repeat that. So what's the difference between these two terms? They look the same. I have capital M, small m, big F, small f, okay? The assumption here is that M will be of the order of lambda. And F, the frequency from one breaking of the shift symmetry, will be very, very big. In fact, it's the biggest scale of the in the problem. Much bigger than, no, not much bigger. This should be roughly the same. Maybe to be more precise, it's like that. That's the hierarchy of scales here. Okay, 1 second. So what you see here, this is big, this is big, this is huge, this is small, and this is small. Okay, I need to also, so F is much bigger, and yeah, this is supposed to be much bigger than small m. This is the hierarchy. That means that if I'm looking at the mass of the Higgs, then there's a constant. There's a term which is oscillating, but it's oscillating with a very, very large decay constant. So if I want to draw this and I have a small resolution, I will not even see that it's oscillating. It will look like it's almost constant because this is huge, okay? If I have cosine phi over f and f is, I don't know, 10 to the 20, and I allow phi just to change a little bit, I'm not going to even see the oscillation. On the other hand, this thing might oscillate very quickly because this f is much smaller than the capital F. All right, that's a hierarchy of scales here, yes?
Can they have different phases, the cosines, and would this cause problems?
What?
The cosines, can they have different phases? So like
Yeah, they can have, generically they will have different phases. The way we'll see it later is that it's coming from two different sectors that break the shift symmetry. It's like if you have QCD1, QCD2, both of them are anomalous, so each of them will give a cosine term. That's one example, yes?
So what exactly are the Fs? The big F is the scale of the explicit breaking of the U1 that leads to the relaxation?
No, this capital F is the spontaneous breaking of the would-be Peccei-Quinn symmetry. Unfortunately, you will...
It's no mass of the relaxation, right? You need explicit breaking as well, if you have a non-zero potential. Like break the shift symmetry.
Yeah, but it's too... so the way the QCD axion work, you have a Peccei-Quinn symmetry, it's broken spontaneously, but it's also anomalous, so then you have some sector which has QCD-like dynamics, which give rise to instantons, and through the anomaly, it give leading to the emergence of the potential. So this is would be replacing in the QCD axion. Here you will have something. So here you'll have something like m pi squared, f pi squared, and m pi squared depends on the Higgs. So here is something of the order of the pion mass, if you wish, of the hidden sector that breaks that through the instantons give rise to breaking the shift symmetry.
Okay,
so there are two sectors, and they are sequestered, so they don't talk to each other. One of them has a much smaller Peccei-Quinn symmetry. But you'll see later there's something which is called clockwork that will tell you the story of the small f and capital F. You'll just have to be patient for now. Any other question? So, okay, you need to understand a little bit how axion physics works, but the good news is that once I wrote this, that's it. I'm done with the relaxation. That's what it does. So now I'm telling you that in here, there's very interesting solution to the hierarchy problem. So let's try to understand why it works, okay? So you see, it's very simple. No voodoo, not like the first third of the lectures from that we had. How does it work? Okay. To understand how it works, we still need to visualize the evolution of the relaxation. So I want to show you roughly how it looks. So this is V of phi. Now let's assume that I start Let's assume that I start the evolution in a place where this m. So for a first go through, forget about this m square. We said that this is small, this oscillates quickly. Let's forget about it. Let's just focus on these two terms. So let me assume that I'm at the location of phi such that the mass here is positive. So there's no electroweak symmetry breaking. Mu squared should be negative in order to see the mass. Now it depends on which sign that I wrote before. But I assume positive mass means that I'm in the symmetric phase. And then when I change mu to becoming negative, I'll break the symmetry. All right. Now, because this f is huge, right? If I'm looking at the field range of phi, which is not very big compared to f, then I'll see that it has almost linear slope. And the field phi, forget about quantum evolution. We will check it later. I promised you yesterday. So let's assume classical evolution. So the field of phi is basically rolling according to this term. Why? Because remember, if I'm in the symmetric phase, then there's no vev of the Higgs. So this term, this potential is not switched on even for the Higgs. So at the beginning, the field phi just evolve and following this potential, moving down the potential. No, sorry, what I said is not true. This is still on. Now, when phi is moving, then basically you can look at this term, and at some point the cosine phi will become, let's say, order 1, such that m squared will becoming bigger than lambda squared. At the point where m squared will become bigger than lambda squared, then the sign of mu squared will switch from positive to negative, and the mass term will become negative, which will trigger electroweak symmetry breaking. So let's assume that there's some critical value here. When this term, okay, let's call it mu squared 0, is becoming 0. So now when phi will pass this point, the Higgs mass becoming negative, and I trigger electroweak symmetry breaking. So here the potential of the Higgs is trivial. Here the potential of the Higgs suddenly has 2 minima. But now, when I'm already in the broken phase, then suddenly this term becomes important. And remember, because f being very small, then this term, when I'm moving, then this term oscillates like crazy. So what I see here is that I start getting oscillation. Now, for now, it looks like this will continue forever. Okay, so the relaxation will just roll down forever. But since we are in the background of all of this is happened in the background of inflation, then we could define a condition for slow roll. So the Hubble is big such that we have a slow roll. So that means that if we look at the equation, remember we have the condition 3 phi dot h is equal to v prime. So if h is big enough, we can be in the slow roll condition such that phi dot is equal to v over 3h. So that means that this relaxation is moving at a very small velocity. And this is the velocity. So for h, if h is very big, the velocity is almost 0. Why is it interesting? Because while it's moving down this potential, if it's at the beginning, it will be just dominated by the slow roll. It will be dominated just by the rolling potential here. But at some point, the potential of the relaxation might develop a minimum. Okay, so it looks like that, and the oscillation the amplitude of oscillation becoming very bigger and bigger because the Higgs wave becoming big. At some point, I will hit a point where the potential, the derivative of the potential is 0, and that's where I'm going to stop as the relaxation. So we can write it. We can write the condition that when v prime of phi will be 0, then the first time v prime of phi will be 0, then that will be the stopping point of the relaxation. So if I'm looking just at the system of equation that I would like to follow, it will look like that. Very roughly, the stopping condition will be given by m to the 4 divided by capital F cosine phi over f. Being equal to small m to the 4th over f. Sorry, this should be sine with a minus. And here m to the 4th over f times sine phi over small f. And so here I have m squared v squared. Okay, what happened is that at the point where the derivative will become 0, what will happen is that this term, which is just, I'm in the region where this term is giving just a falling potential, will exactly be balanced by that term. Okay, so this is the equation that satisfies v prime equals 0. V prime phi equals 0. Okay, now why did I put the v squared here? Because this is called the back reaction potential. Remember that this term is the coefficient for the term h dagger h. So it depends. The potential has h dagger h in front of it. This is why it's only switched on when the valve of the Higgs is on. This is why you have here v squared. Okay? Any questions? Yes?
When do we get the linear decline that you eventually get from like a very high phi? So for high values of phi, we have this linear slope.
Yes.
Where does it come?
It's just coming from basically this term. So if you look at, you need to start at some region where cosine phi over f is basically negative. And since, if you look at the cosine phi over f, it has the shape of a cosine. There are big region, because f is so huge, there are big region where it's just falling and you can think about it as linear. And if you just throw a dart in cosine phi over f, there's order 1 chance that you'll be in this region where it's just falling.
So we don't start at phi equal to 0, but just the...
We start as just generic point in cosine phi over f, yes. You don't start at 0, you don't start at pi over 2, you start at generic point. Or let's say that for the relaxation mechanism to work, you need to start at this region where it's just falling. But there's a big chunk of parameter space where it's falling. It's like a probability of a half or something to be there. So that's the basic assumption. Yes?
We start from a point where the cosine is order 0, right? Because you want the u squared to be positive, but then you want to describe the state transition point. So the field phi has to have an excursion of order f.
Yes. Yeah, that is true.
Okay, so then you would see the cosine. It's not
No, order f means like, 2 pi over 4. Doesn't matter.
Still, it's definitely not linear. You see a chunk
No.
of
It's, it depends on the ratio now between m squared. If this is 2 times bigger than that, then you already have a region where it's linear. All that you need is this to be a little bit bigger than that. And that is fine.
That's number one. Number two is I don't understand. So is the relaxation potential this, or is it also like I don't understand this back
Everything.
reaction, the back
Everything.
reaction of the Higgs on the potential?
So the relaxation of every function which depends on phi will affect the relaxation, right? So this has h dagger h times phi over f. So if I'm solving the equation of motion for phi, definitely I need to include those terms. Okay, and the other question is really simple, so you can think about it and be convinced that it's correct. All that you need is this term to be just slightly bigger than that.
So the last one is why do you necessarily stop at the first point with the potential?
So that depends how slow you are, but in the limit where h is big, and we will check this, maybe not, but you can check that if h is big enough, then you won't have enough kinetic energy to pass the first. Okay, so that's a simple condition. Now, how is this even solving? Yes?
I still don't get why we have this limit. So we start with a simple cosine potential of phi that does not care about the Higgs. So
Yes.
how does it come?
But when you're passing through the point where mu squared change its sign, so basically when you pass through mu squared equals 0, which will pass generically, again, assume that this is 2 times bigger than that. And you start at a point that this is smaller than that, then you'll just get positive Higgs mass. But when phi is evolving a little bit, maybe you will pass this m squared. You'll have cosine phi over f times m squared that is slightly bigger than lambda squared. And then the Higgs mass will switch its sign to negative. You'll trigger electroweak symmetry breaking, and you will suddenly have the Wiggles, which is growing when the wave of the Higgs is growing. So when this is evolving, this becomes more and more negative. So now the amplitude of the Wiggles increases because they are proportional to v squared. Okay, you'll have to draw it to yourself and get convinced that I'm not fooling you, but you need to maybe work a little bit about that. Yes?
At what point does the u squared parameter goes into v of phi? This is what this question is referring to.
At what point again?
The u squared parameter, at what point is it occurring in v of phi in the potential that you draw? Because if you want
This one is very roughly when m squared cosine phi over f is just equal to lambda squared.
No, I mean, if you cross the point where you have the electroweak symmetry breaking, what changes in the potential domino? Is it the cosine? Is it the m to the 4? What is it?
No, the m to the 4 doesn't change. This is Higgs independent. The stuff which depends on the Higgs and is relevant to the Wiggles with the low frequency is this one. Okay, because suppose I add to the Lagrangian a term h dagger h cosine phi over f. Yes? Then when the wave of the Higgs is 0, then this term is not important. But when the wave of the Higgs is positive and growing, then this term becoming important.
But this does not occur in the potential down below.
No, this continues. This is always there. This is independent of that. But I have also this term. Look, maybe I didn't explain it. It's at the end of the day, it's very simple. So v of phi is m to the 4th, let's say, cosine phi over f. This is independent of the Higgs. It's always there. It's called rolling potential. But then I have the other terms. Let's say h dagger h cosine phi over f times m squared plus m squared cosine phi over f.
Okay, now I see. Because it wasn't like conventional on the board.
Yes.
So now there's this back reaction.
What's that? So this is we call back reaction just because it has very low frequency, so it oscillates very fast.
I think now it makes sense because how is reflected that potential? That should just behave like it's drawn at the very beginning without the small wiggles.
Yeah. Yeah, so at the beginning there are no wiggles. So at the beginning it's just rolling because of the cosine phi over the f. And then you switch the mass and then suddenly you get the wiggles.
Exactly, but this is not included in that potential.
No, no. Because usually this is the Higgs independent potential is calling just the rolling potential.
This is the complete.
Yeah, this is the full one. Okay, there's a mixed terms and then the pure term. The pure term is called the rolling potential. All right? Yeah, sorry about that. Now, I still didn't tell you why is this even has anything to do with the hierarchy problem. How is this related to the hierarchy problem? This is as follows. Let me start with lambda, which is very big. I cannot take lambda to be as big as the Planck scale, unfortunately, but let me assume that lambda is much, much bigger than 100 GeV. I don't know, lambda, let's say that lambda is 10 to the 18 GeV squared. So this lambda is well above the weak scale. So my initial condition is that lambda squared is much, much bigger than the electroweak scale, v squared. So as we discuss all the time, here you have all the contribution from the UV physics, and the naive mass of the Higgs should have been very, very big, of the order of lambda squared, in this case positive even. All right, that's what you expect in natural theories, that the bare Higgs mass is of the order of the cutoff squared. If I can convince you that we arrange through this evolution that when phi stops here, at the point where it stops, somewhere here, then this combination, this we can even forget because it's very small. If I can convince you that this combination, mu at the stopping point, so let's say mu squared at phi stop, where phi stop is much, much smaller than lambda squared, it means that even though I started with universe where the Higgs mass is very, very big, I will end up through the cosmological evolution with a point that the mass of the Higgs is at the weak scale. Remember how I defined in the first lecture what I think about naturalness? I want to have a well-defined relation between what's happened in the UV and in the IR. So here, the UV and IR is replaced by cosmology. Now we see the mass of the Higgs very small, but originally the mass of the Higgs was generic. And if I can see through this basically relation that indeed I'm satisfying this, it means that I solved the hierarchy problem. So today, because of cosmological evolution of the relaxion, we are living in a universe where the weak scale is very small, even though fundamentally it's actually is characterized by a cutoff which is very high. That's how it solves the hierarchy problem.
Two questions. First of all, what about tunneling probability to other minima?
Yes, so you can actually convince yourself that I think that we're not going to do this, but in principle you can look at the quantum evolution versus classical evolution, and you can prove that if you are dominated by classical evolution, at the same time, the tunneling is becoming exponentially small. So the probability of tunneling is something indeed I should be worried about, but it's very, very small.
It's always exponentially small.
No, it depends on the parameter. It could be, you can have e to the minus something which is very small, so then it's not exponentially suppressed. But in this case, you can easily convince yourself.
It gets worse stability than in the Scalar model.
Yes, it's the lifetime of the relaxion from one minimum to another minimum is very, very long.
The question number two is, why do we need an inflation back onto this picture? You didn't use the...
No, I use this in one important relation to say that it's slow rolling. I need to get rid of its kinetic energy such that at the first minimum, it will stop.
It's slow rolling because F is big, but we didn't...
No, the relaxant is slow rolling because it's in the expanding universe. So the Hubble, when you write the equation of motion for the relaxion, all of this was V. That is the V prime. There's always phi double dot minus 3h phi. Yeah, I wrote it somewhere here. This h is from the inflaton sector. So I'm in a rapidly expanding universe because it's during inflation, and this is satisfied that the velocity of the relaxion is small. Everybody feels the Hubble, right? Hubble is universal, it's gravity. So it's also slowed down the relaxion, not only the inflaton.
You don't need Hubble to exponentially grow, you just need it to be big, but the Hubble is static in something. It doesn't need to grow.
No, if Hubble is constant, it means that the universe is exponentially expanding. Hubble is a dot over a, so for Hubble to be constant, it means that a is e to the v over m Planck square. Okay? So constant Hubble means accelerated expansion. Any other question about this? Okay. So now what we need to do is actually to see what we have in what this relation is telling us. Now, we already said that we are in a random point of the parameter space of the big potential, the one with capital F. So I can really just translate this relation to the following generic relation that basically m to the fourth times f over f is equal to basically v squared m squared. So this is the m, the capital M and the small m are related to breaking of the shift symmetry from a QCD-like dynamic, which is, the QCD scale is a technically natural parameter, right? It's protected by dimensional transmutation. We are not worried about why lambda QCD is 100 MeV and not M Planck because it's protected by the beta function, right? So it's a technically natural parameter. So M and small m and capital M are parameters that I can control, and they will not receive big radiative correction. And small f and big F are related to the spontaneous breaking of Petchy-Quinn-like symmetries. So again, they are generic. I can control them, which means that the V squared, which is just linear combination of all of this, is a technically natural parameter. And therefore, if I have the right relation between these parameters such that this is very high, let's say this is 10 to the, M is 10 to the 9 GeV. This is exponentially large. We'll discuss it in a second. This is of the same order as M. Then I'm arriving to a situation where despite the fact that the M is of the order of lambda and is very big, then the VEV of the Higgs is very small. So this is why, indeed, it solves the problem. Okay, I start with the generic. I will let the universe evolve. The relaxon will evolve. And because of this combination of parameters, the weak scale is very, very small compared to the cutoff. That's it. This is how we solve the problem. Now, there's a problem, though. So this is working. OK, this is fine. What I told you so far, it's OK. But there's one issue with the scaling here, which is funky, and I want to show you. M squared, if we want to keep the theory natural, this small m squared, it needs to be smaller than the weak scale. Why? Because when I look at what's the easiest way to show this? So here I have a potential which looks like m squared h dagger h times cosine phi over f. If I'm closing the Higgs loop, I'm going to get contribution to the back reaction potential, and I don't want the wiggles coming from closing this Higgs loop, so it looks like that. M squared cosine squared so it looks like that. I have here cosine phi. Here I have the Higgs loop, and here I have cosine phi over f. And this is the Higgs loop. So I basically, I insert twice this operator to the Higgs loop. So I have it here and here. When I do it, I see that I get a contribution to the back reaction potential of the order of the cutoff of this loop, which means that if m is much bigger than the weak scale, I will get Higgs-independent wiggles that will destroy the relaxation mechanism. So from that, maybe it was too quick, but you should believe me. For that, I'm actually concluding that m squared should be less than v squared because of that loop contribution. So that means, let me set m to its upper bound, to v. That is telling me that v to the 4 over m to the 4 is equal to small f over big F, which means that v goes, or v is bigger always from m to the 4th, sorry, m times, no, sorry, v is always, bigger than m times capital F divided by small f to the power of 1/4. No. Sorry. Once again. Yeah, so F over F power of 1/4 times capital M. Okay, that's the crucial, basically, relation of the relaxation. What I see here is that the electroweak scale is proportional to the cutoff of the theory, so this is capital M, times the small frequency divided by the big frequency to the power of 1/4. And this is a very bad scaling. So I remember what I want to show you is that I can make V much smaller than M. This is if I may have a successful relaxation mechanism. So I need this to be much smaller than that. Let's say this is 10 to the 9 GeV. This is 10 to the 2 GeV. That means that here, the ratio between F and F, small f and big F, is exponentially large. So let's just write it explicitly. Suppose I want V to be 10 to the 2 GeV, and suppose I'm having M of the order of 10 to the 9 GeV. Then this is telling me that F over F needs to be basically 10 to the minus 7 to the power of 4, which is roughly 10 to the minus 28. So that means I somehow need to arrange that I have two sectors that break the Pecchy-Quinn symmetry, where the ratio between the decay constants is 10 to the minus 28. Or in other words, when I say that I have one capital F, which is almost constant frequency, and then I have small f, which is oscillating rapidly, I took it on steroid. Okay, that means that over one period of the capital F, this is doing 10 to the 28 oscillation. So this is really crazy, right? When we, for example, when we think about regular QCD axion, then the bound on F, you know what it is, the bound on small f? Typically, small f needs to be bigger than 10 to the 9 GeV from star cooling. So that means if small f is 10 to the 9 GeV, capital F will have to be 10 to the 37 GeV. And that is totally crazy. Okay? It's also against what we discussed, that we don't want to be sensitive to Planck physics, and the capital F looks to be humongous. Okay? So I have till 12:45. So I will not, okay. I think I will not go through clockwork, unfortunately. So there is a nice construction, which is called clockwork, that allow you to, instead of having small f and big F as fundamental parameters, you have only f, small f as fundamental parameter, but then you need many sites. It's in the notes, or you can read the paper, which show you how to arrange these huge hierarchies. But the bottom line is that if we want the relaxation mechanism to be realized, we need actually two sources of oscillation. One is oscillating with very rapid frequency, maybe 10 to the 9 GeV, and the frequency of the other effectively needs to be exponentially larger to that. In this case, 10 to the 37 GeV. How to arrange this without having physics beyond the Planck scale is through this clockwork mechanism that I will not be able to show you. All right? So in the last 15 minutes, I want now to relay this to experimental observation. Yes?
Where was this capital M equal to 10 to the 9 GeV coming from? Is this just a random choice?
No. So the highest possible, so last time I promised you, but I didn't have a chance to show you what are the implications of required classical evolution. So in fact, if you want to require the relaxant to go through classical evolution and the inflaton to be dominate the energies, you have two inequalities. And this is telling you that the highest cutoff possible of this theory is of the order of 10 to the 8 or 10 to the 9 GeV. You cannot really take it above this. So I want to show you the realistic parameter space. Yes?
Okay, just to make sure, to get the two different constants, we need, like you said, we only need to add one scale of the state relaxant, but we also need to add two different sectors
That break the shift symmetry.
don't talk to us and also don't talk to each other.
Yes.
Independently break this.
Yes. And all of this you can achieve quite simply with this clockwork mechanism. Okay? If you like model building, this will give you an appetizer to look at the paper. It's not very complicated, by the way, but we don't have enough time. Yes? What's that? So that's a very interesting question. So you can be even more sophisticated and analyzing a little bit more carefully where is the stopping point. This was done in a paper by collaborators at Weizmann, which we call relax relaxion. And there you can prove that the first point where there's a minimum, it's actually when phi is equal, phi over f is exactly equal to pi over 2, up to very small correction. So axion, which stop at pi over 2, is not a good axion. You want the axion to stop at, or theta bar minus a is pi over 2. You want a over f to be exactly theta bar to cancel to have a zero strong CP. Here you have a precise prediction that the phase here is pi over 2. This is why if you look at the original GKR, the relaxation paper, they say that it's not a good solution to the QCD problem. In fact, back then they didn't know that it will be exactly pi over 2. And there's an attempt to solve this. There's a paper by Ann Nelson. Unfortunately, she's not with us anymore that tried to solve this. But that paper needs to basically deviate from the assumption of a classical bits quantum. So there's quantum evolution, which leads to problem. If you wait for 1 week, you'll see that there is a solution to that problem. Okay? So yes, you can solve the strong CP problem with that. But you need something else. Yes?
How many of these new energy scales are actually independent? And are they like constrained by the
Yeah, good. By the way, maybe in the discussion tomorrow, I'll talk a little bit about quantum sensors because I think I will probably just not get to that. So the energy scales which are involved, which are independent, are as follows. So we have small f and big F. This we said this will require clockworking. We didn't explain, but you need huge hierarchy here. So that's 2. Then you have capital M and small m, which related to 2 sectors that break the shift symmetry independently. This is called sequestered sectors. So they don't talk to each other, and they break the shift symmetry. As if you would have in the standard model the QCD sector, and then another sector which are anomalous will give rise to the axion potential. So in fact, we need 1, 2, 3, 4 in order to explain the smallness of the weak scale.
So one is bounded by cosmology for the axiom, but the others you can take whatever you want.
Yes and no. So this, as we said, needs to be smaller than the weak scale. And there's also bound on that. It needs to be less than of the order of 10 to the 9 GeV because I'm assuming that it's the same order of the cutoff. So there's a range for them. OK. So now we want to take the next step and to understand the phenomenology. Because all this relaxation now mechanism, so suppose that you bought everything that I fed you. Okay, you need to think about it. I know it's, if you never saw it, it's hard to understand. But suppose that it works. Then we have a task, right? Like we were looking for supersymmetry at the LHC, TeV new physics. Now let's try to understand the phenomenology of this simple potential. Okay, it's not complicated. At the end of the day, it's just 2 lines with some story that you need to digest, but 2 lines. And they are telling you that there's some coupling between the relaxation and the Higgs. So there's potential which involves both the relaxation and the Higgs, and maybe some shift symmetry breaking, and that's it. So let's try to see how we can search for this phi. And the way you search for this phi is because of one interesting property that it has. And to understand that, it's enough just to consider one term. So I will just highlight one term. So let's do, here maybe we'll keep. So let's, now I want to understand the phenomenology of this theory. And in fact, it's not very complicated. Because, again, I'm starting with the Lagrangian, and I want to introduce only one term. Yes? Typically, star Cooling bound, if the reaction coupled like an axion, you see the axion? The star Cooling bound will say that F is bigger than 10 to the 9 GeV, or 10 to the 8 GeV if you push it, yes. So F needs to be pretty big. By the way, I'm going to talk about the non-trivial reaction phenomenology. If the reaction is really the axion, we have all the axion phenomenology. So there are many ways to search for axion. You'll hear all about this with Raffaele. Now I'm giving you the unique phenomenology. And also, it doesn't have to be the QCD axion. So let's look just at what I call the back reaction potential. This will tell you 90% of the new phenomenology. It is basically just given by that. Okay, this term is giving you almost all the story of how to search for the reaction. Because when you look at that, and you remember that the stopping point is phi, roughly it's pi over 2, then you see that if I will look at the mass square matrix of the axion and the Higgs, then here I have the Higgs mass squared. Here I have the reaction mass squared, which is, I will write it as m phi. And here I have something which is mixing. And let me just tell you that what I'm doing now is naive. So I'm not introducing this pi over 2 business. So naively, when I will look at this matrix and we diagonalize it, I'll see that m squared reaction is very roughly equal to m squared v squared over f squared. So that's very similar to axion. In fact, it's smaller than that. Okay, there's some suppression parameter that I don't have time to discuss. And also, there's a mixed term, b mu phi, b h phi, which is just coming from one derivative with respect to phi and one derivative with respect to Higgs of this potential. So it is given by, again, I don't care about factor of 2 here. It's very roughly given by mv. What am I missing here? M squared, sorry. M squared V over F. This is telling us, this term is very important. What it's telling us that there is reaction Higgs there's reaction Higgs mixing. So when you diagonalize this matrix, you actually find that there's a sinus theta, there's a mixing angle between the Higgs and the reaction. Which is very, very cool. Why it's very cool? Even if I do all the shift symmetry, all the action story in some hidden sector, not the QCD, so it's not coupled even to the Standard Model, still one thing I have guaranteed, that the Higgs and the reaction will mix. And that means that because Higgs couples to all the Standard Model fields, up to sinus theta, and this sinus theta naively, again, I don't want to confuse you too much. This sinus theta, you can prove that it's smaller than m over v. And there's also upper bound on that. So if you are looking at Higgs phenomenology and you multiply by this sinus theta, you actually get to the reaction. Okay, so that means that you have you can think about the relaxion as a model of Higgs portal. Okay, it's a model of Higgs portal is just model when you have a scalar, which would be the relaxion, which couples to which mixes with the Higgs. So the minimal Lagrangian, the effective Lagrangian of this theory can be given by the mass of the Higgs plus the mass of the relaxion, and then plus a cubic term that is related to this mixing, which I can write as mu s h dagger h. And from that I can extract actually the mixing, and that's it. Now, what is very fascinating is that once I make this f very big, then the relaxion has become super light. Okay, so if this f is big, then the mass of the relaxion is very small. So typically, we expect that we will have a very light relaxion. Which means that the phenomenology of that is very similar to the phenomenology of light axion. But instead of having axial coupling, instead of looking for it with magnetometers, it's actually behave as a scalar. So this is a theory which naturally speeds up a very light scalar. And it can even be a dark matter. So it's as if we are living in a background of oscillating relaxion, oscillating dark matter. But instead of being axion, it has scalar coupling. And therefore, it leads to a fascinating set of phenomenologies. Okay, you can search for it with equivalence principle or with quantum sensor, and that's what I will quickly describe maybe tomorrow. And this is it. Thank you.
That was a lot to digest.
Yeah, yeah.
So you can read the material, and then tomorrow Gilad will be here for discussions. But if there are any questions now, yeah, I have 2 questions there.
So if you add this very light scalar, how does it affect oblique parameters? Is there any sizable correction?
When it's very light, it means that this f is big compared to m times v. So that means that the correction to electroweak percentages are super small. Okay? So it's tiny. If it's heavy, then you can search for that. Okay? You can get bounds from the Higgs, etc. Not necessarily from the W and Z, but you can search for Higgs decay to this phi, and you can look at Z, which branches along this phi. So there's a variety of searches that you can do. If it's a bit lighter, you can look at this at beam dumps, LHCb, Na62. So there are a host of bound that you can derive on it. I will briefly show it tomorrow.
Thank you. Yeah, very technical question. So when you derive the mass of phi, you're doing true derivative on phi, so it looks like you're expanding about phi equals 0.
Not necessarily. If I will, here I kind of expand it around generic phi. Any generic phi will give you that. If I will try to do it around pi over 2, I will, of course, get 0. So I need to understand the correction beyond pi over 2, which indeed leads rise to the fact that there's another suppression factor here, which is very interesting. It's of the order of mu over lambda. What I call here mu is, I think, m over lambda. So that's the true mass. Now, because of this factor, you get something truly amazing from the point of view of naturalness. The mixing is not suppressed by this parameter because the mixing is proportional to sinus. Sinus pi over 2 is not small. So the mixing, while the mixing is kept fixed, the mass is smaller. So if you are looking at observation, because the mixing is telling you how the relaxation interacts with the field, you see that the coupling to the fields is big for a fixed mass, which looks like evident violation of naturalness. And this is why we call this relaxed relaxation. So the relaxation not only explain why the Higgs mass is so small compared to the cutoff. It's also have a self-explanatory why the reaction mass is much smaller than what you expect based on naturalness. Okay? So it's very weird beast.
Thanks.
More questions? Okay, well, let's thank Gilad for a series of lectures. And we have special bonus time with Gilad tomorrow, but then we'll see you at the colloquium at 2 o'clock.